So now coming on the attacking reagents, that what kind of attacking reagent does the substrate can encounter. So we have basically 3 types of attacking reagents, right. So what is that? The first one which we will be taking on is free radical. Other can be an electrophile, means they can actually attack, and we can have the nucleophile. We can have the nucleophile also. So the first I am taking on is the free radical. As you are familiar with the free radical, as I told you in a previous lecture or when we were discussing this reaction mechanism, when we were discussing the bond cleavage actually. So what is free radical? It is an atom with unpaired electron. It is the atom with unpaired electron is called as free radical, right. For example, and we know that how it results, actually it results from the, as a result of from the homolytic fission. It is formed as a result from the homolytic fission. And what's that? I told you, suppose I have this thing, the bond gets cleaved in this way, that this takes 1 electron of the shared pair and this also equally take the 1 electron of the shared pair. So this is something called as free radicals. These are called as free radicals. Let us look for some example. Suppose I have Cl, we know Cl exists as Cl2, so there is a single bond formed between them. It gets cleaved in the presence of light in such a way that it forms the chlorine free radical, right. Likewise, we can have, suppose I have methane, it gets cleaved in this way that we get methyl radical and the hydrogen free radical. So actually these free radicals formation is favored by heating in presence of UV light or general light. So these factors actually favor the formation of free radical, and obviously I told you it results as a result of homolytic, it is formed as a result of homolytic fission. So if we look for the hybridization of the carbon present in this case, so you will get to know that it is actually sp2 hybridized. It is actually sp2 hybridized and the structure is something planar. And if you have any doubt related to this, you can consult the chemical bonding chapter where we have discussed all the hybridization sort of things. So this is what is, it is sp2 hybridized. And if we talk of the stability, now my concern is that I want to know about the stability of free radicals, that how they are stable actually, right. So when we look for the stability, what we have seen that the tertiary carbon is more stable than the second degree, then the 1 degree and from the methyl group. So if we talk about, we are talking about the free radicals. So if there is a free radical, tertiary free radical, a secondary free radical or 1 degree or in methyl group, which is more stable? The 3 degree one. 3 degree one is more stable and this methyl is least stable. Now what is the reason that determine their stability, or why I am saying like that 3 degree is more stable and methyl is something not stable, least stable? So we can actually discuss the stability on the basis of many factors. So the first factor I am taking into consideration is the bond dissociation energy. I am taking the factor is bond dissociation energy. See, breaking of bond, we know that whenever we need to break the bond, we require a bond dissociation energy, right? And lesser the energy we require to dissociate a bond, stable is the free radical, right? Again, if we have a substance like that where we need to give, obviously for the breaking of bond we need to give energy from outside, right, and the energy merely depends upon the attraction between them. If the attraction is high, you have to supply it with more bond dissociation energy, and when you supply it with more dissociation energy, it corresponds to the lesser stability of the free radical, right. So likewise here, when we talk of 3 degree, so bond dissociation energy which is required is least because attraction is minimum. So that is why its stability is maximum, because it required less amount of bond dissociation energy. And if we talk about the methyl group, then here in this case the bond between C and H is something strong, It is something strong. So that means we need to supply it with more bond dissociation energy. And when we supply it with more bond dissociation energy, it corresponds to the lesser stability. So we will say that it is least stable as the force between C and H is good enough. So that is why we need more bond dissociation energy. So when more bond dissociation energy is required, it corresponds to the least stability. Right. So this we can explain on the basis of bond dissociation energy. There is one more factor which we can use to explain the stability of free radical, and that is something called as hyperconjugation. We have already discussed the facts, that is the kind of electron displacement, the inductive effect, the electromeric effect, the resonance and the no bond resonance, that is the hyperconjugation. So this we can actually explain on the basis of hyperconjugation. You know that if the carbon is bonded to more carbons and they have the hydrogens, so 3 degree will be something like that. So what happens? So 3 degree will be something like that. So they will have more alpha hydrogen. We know that for this carbon, this is an alpha hydrogen, this is an alpha hydrogen, this is an alpha hydrogen. So that means how many alpha hydrogens we have? 9. So 9 alpha hydrogen means 9 hyperconjugative structures. So that means more delocalization of electron. So when there is the more delocalization of electron, which can be merely due to presence of more alpha hydrogens. So again, see, more alpha hydrogen means more hyperconjugation. More hyperconjugation means more hyperconjugative structures. More hyperconjugative structure means that there will be more delocalization of electron, and that something corresponds to the stability. So what we have seen in this case, when we talk of 3 degree, there are 9 alpha hydrogens. Here there are lesser than that, and here it less, and here it is only 3. So that means what out of them which is more stable? Obviously the 3 degree one, because they have more alpha hydrogens, and more alpha hydrogen corresponds to more hyperconjugative structures. More hyperconjugative structure means more delocalization of electron. More delocalization of electron corresponds to the more or a maximum stability. So this is what is the free radical. I think you got it, that free radical is something, an atom with an unpair of electron as a result of homolytic fission. They are formed in the presence of heat, UV rays or light, simple light also. And as far as the stability concerned, so we can explain on the basis of bond dissociation energy and hyperconjugation, and which free radical is most stable. Obviously it is the 3 degree one, and which is the least one? It is the methyl group, right? So you can explain on the basis of hyperconjugative structures and the bond dissociation energy. So now we will start with the second, this we have already done. Now we will start with the electrophile, right? So just look at the board.